the table. And then he'll grab it if he needs. I'll forget.
Okay, before we take up any more time, we'll commence this evening's lecture. We're here, July, and this is apparently what we're talking about, something to do with weather forecasting and task setting. We'll work it out between the two of us anyway. Originally we intended Alex Wallace, who's a guru on weather models, to be here talking about weather models and use of those. Unfortunately, he's spending most of his time in China at the moment, so he's over there and therefore have to put up with me in pro. So that's today. Now, we have a problem next month, and to some extent the month after. Mr. TBD is up here quite a lot. So firstly, I don't have a presenter for talking about thermaling. So we had, so last month before, we had Grant Hudson talking about thermals in terms of the formation of thermals and characteristics of thermals. But this is how you actually fly thermals and how you fly thermals with other gliders is the kind of the intent on that. But I'm looking for volunteers for somebody to actually, I'm tapping a few people on the shoulder, but I haven't had any success just yet on that. So that's on that. And then I'll be talking about flight analysis, primarily using CU next month. The other problem next month is that we don't have a venue just yet. Still working on that. If anybody's got any bright ideas, let me know. So we're working on some through Adelaide Uni as a possibility, and also there's a couple of other areas that I'm looking at as well at the moment. So hopefully we can get that sorted out in the next week or two, and I'll get the message out as to where it's actually going to be. Don't turn up here; it will not be here. Which is unfortunate. It's a really good venue, but it's not available on that night or those 2 nights. Okay. So on to our first speaker for this evening, who is Craig Vinyl. And I've inflicted on him what I've inflicted on everybody else. I've asked him for a bit of a bio or a CV in terms of his background, which I always think is quite helpful. And he's gone to great pains to actually say that he's not a lawyer. He's actually a patent and a trademark attorney. Apparently that's not a lawyer, but anyway. And I was surprised to find out he's got a degree in mechanical engineering. He's a senior partner at Maddens here, and it's of course through his goodwill that this room and facilities have been made available to us. Getting onto flying, he started flying at Waikerie in 1997. Relatively big, less than 20 years. And achieved an awful lot in that period of time. He wanted, what does it say about that? Started flying Waikerie in 1997 for something to do while spending a week with his parents who recently retired to Waikerie. Found a good hobby. Went solo in 1 week. Led on the war flying, basic cross-country courses, coaching weeks, badge flights. At that time, the longest being 600 kilometres in the Club Hornet. Which is a pretty good flight. He vowed never to fly in competitions. A few of us have said that. However, his first competition was the Club Class Nationals in 2005, and he's competed in quite a few competitions since then, so he's obviously got the bug. So the Multi-Class Nationals, Sports Class Nationals, South Australian State Comps, and Horsham Weeks, lots of them. Previously owned a Mosquito, did a 750k flight in the Mosquito. Now owns Victor November Lima, which is an ASG29, the turbo, the ASG29E. And he's done 2 1,000 kilometre flights in that glider, which is a good achievement. And what's really remarkable is he did a flight at the 2010 Multi-Class Nationals at 174 kilometres an hour. Now that wasn't a short flight either. I mean, what, 500 kilometres at 174 kilometres an hour. That's pretty impressive. He likes doing the Club of Pounce at Waikerie. Loves that apparently. When he's not doing that, he can be found in the Adelaide Hills, on his bike, or searching for that perfect bottle of wine. So I'll hand over to you, Craig. And yes, well, we'll change the electronics over. Basically, the way we'll run this is that he's going to start off talking about the physics of the boundary layer physics of the weather, as far as you know it. I'll take over for 20 minutes, perhaps half an hour, talking about some of the weather models, their origins, and how we use them in gliding. And then we'll, depending on how the timing works, we'll go for a break after that, and then finish off. Craig going to talk about task planning based on the weather we've just sort of been through. So we'll swap the electronics over.
While Peter's swapping over, I have to apologise for the next 2 months not being here. I just couldn't, well, I'm on long service leave, so I take off next Tuesday for warmer climates for 8 weeks. So unfortunately it takes me out of this location for that period of time. And I had, I think the topic that I was meant to be talking on tonight was weather forecasting. But rather than try and cover such a large area or large field, what I wanted to do, and I think I may well be talking to people here who both A, know what I'm talking about, and B, are probably more expert than what I am. But hopefully and certainly there will be people in the audience who are perhaps newer to gliding that might benefit from perhaps some of the things that I say tonight. So hopefully, and by all means, if you've got any comments, then please chime in. But we always look at this diagram, or at least used to, I suppose, when we had temp traces, perhaps less so now. And there's some things there because of my mechanical engineering background and thermofluid dynamics that I did that I kind of had an intuitive understanding about, particularly when it came to things like the dry adiabatic lapse rate, wet adiabatic lapse rates. But it probably doesn't hurt to perhaps look at some of those things, particularly for people that maybe don't have a background in that sort of area, just to understand some of the physics that occur in relation to the boundary layer, and looking at this relationship that we have between pressure and temperature, to look at things like humidity, and to just look at what we mean by dry and wet adiabatic lapse rates, and how that ultimately affects this particular diagram that we see, and hopefully give some guide to what Peter's going to talk about, which was ultimately the height that thermals go to and where clouds form. So that's really what it's all about. So first of all, those of us that have done first year physics or any form of physics at high school or university would have come across this. Often it's called Boyle's law, but that's not right. It's actually a combination of two laws. It's called the ideal gas law, and basically what it says is that there's a relationship between pressure and volume of any particular gas, and the gas mass of the gas involved, its temperature, and this particular gas constant, which is dependent on the type of gas consumed, whether it be natural air or it's say argon, for example. But what we're really interested in as glider pilots are the P and the T, and what that equation really says is that P is directly proportional to T. And what that means is that if the pressure decreases as the air goes up, then the temperature decreases, directly related. And similarly, as pressure increases, then the temperature goes up. Now, one way to think about this is, and we've all probably done this, if you've got a bicycle pump and you're pumping away, what happens at the end of the pump? It's hot. That's right, exactly. And that's how diesel engines work. It compresses the gas will get to a temperature where it will ignite the fuel in there. So obviously, as pressure increases, the temperature will increase. And likewise, for those people, I use little CO2 cylinders when I get a flat tyre on a bike to pump those up. And one thing I'll be really careful of is grabbing hold of a glove first before you let this thing go, because it'll freeze if you've got your hand tap attached to it. So basically, decreasing pressure will result in a decrease in temperature. So it's pretty clear. I don't think there's anything controversial about that. But what that really means for us is that rising air cools, but also descending air will warm. Now, certainly, if there's a parcel of air sitting on the ground that's heated to a temperature which gets above the environmental temperature, that air becomes buoyant and will start to rise. But of course, as it rises, it cools in relation to what is called the dry adiabatic lapse rate. But similarly, you can have circumstances where descending air will also heat. And I know there's probably people in this room that might have a theory about this. When you have a standing wave set up, say a shear wave, what you have is effect descending and rising air, so that in these regions, as that air is descending, you get a region here which gets a little bit hotter. When you've got air that's rising, you get air that's a little bit cooler. So I think we've all experienced maybe those days where you're flying cross country and all of a sudden you come to an area where it's dead, you can't get yourself going, and then you get a few kilometres along and all of a sudden, bang, it all booms again. That's potentially, well, I've heard that theory before. I don't know if anyone's has had similar experiences. Does anyone agree or disagree with what I'm saying? And obviously where you have...
I agree with the observation.
Yeah.
But you do have, I think, it's weight influence.
Yeah.
Where you get areas of rising air and other areas where it's a lot is not happening. You need to be really good with this. I'm not sure it's because of the temperature difference, though. I think the temperature difference may go with it, but I think it's actually it's the descending air, which is like in a low pressure system or something, where the descending air is going to create some issues.
But I suppose talking about what I thought was high pressure systems and subsidence, we have descending air with a high pressure system, then that's probably, if it's not descending all the way through the atmosphere, then you may give rise to an inversion as a result of that, where the temperature actually increases as a result of that subsidence or descending air. So again, but it all gets back to this relationship of pressure and temperature, so that what we've got to remember is that that gas law will always work such that decreasing pressure will result in decreasing temperature. And traditionally, we worry about ground-based convection, and certainly as that parcel of air becomes buoyant and starts rising, then clearly what it's going to do is its temperature is going to decrease, and it's going to decrease at a predetermined and known rate. Another aspect to consider for glider pilots is humidity. I was going to bring it out, but one of the things I did in engineering fluid dynamics was that we had a table, which is a graph, which was the various states of water and temperatures and pressures. Basically moisture or water, H2O, can exist in three forms. It can exist as a solid, ice, it can exist as fluid water, and it can exist as a gas, a clear, invisible gas. And of course, right around us right now is water vapour. And of course, on a hot day when we're looking for 10,000 feet, we hope to be at 10,300 Q. Well, generally speaking, if you have a relative humidity of around 15%, by the time it gets to 10,000 feet, that air mass is going to, as it rises, will cool, and will obviously cool to a temperature where it reaches 100% relative humidity. In which case then that parcel of air, the air around us at the moment, I imagine the air would be very close to being saturated at the moment because of the weather conditions we have. So, a volume of air at a particular temperature can hold a certain volume of moisture. If you heat that air can hold more moisture. If you cool that air, its potential to hold moisture reduces, and it reduces down to a point where it's at 100% relative humidity. And at that point, it can no longer hold any more moisture. The moisture will start to condense out of that air mass, and that's what we see. It's a cloud forming. So obviously, in the case of this particular diagram, which I'm assuming everyone's familiar with, which is the environmental lapse rate is the blue line. Obviously, as we cool our parcel of air, when it hits the dew point, which is the green line, you're going to have a cloud form, because it's simply reached a point where that parcel of air can no longer hold any more moisture. The moisture has to come out of solution effectively, and so you get condensation forming. We've all experienced that in bathrooms, cold conditions with mirrors that will have condensation forming on them, for example. Moving on, then we've got a few terms that that we normally use. Environmental lapse rate is the blue line, and basically that's the temperature of the atmosphere without any change, without any heating that occurs and the mixing that occurs. But if you took a snapshot at a particular time of the day, then you're going to have this temperature profile, and obviously it varies, you know, depending on whether or not a cold front's come through and a new air mass has come in with a cold air that would affect 5,000 feet and below. But generally, the environmental lapse rate is somewhere between 1.8 and 2 degrees per 1,000 feet. And of course, as I said, that can vary depending on the sort of the heating as the high pressure system moves in and the temperature starts to increase and the wind for South Australia starts to swing to the north and northeast and norwesterly, then obviously that temperature profile, as we know, this will all fill in and you'll get a blue line that's around here somewhere, and provided the heat of the day gets out past that trigger point, then bang, the day will really go. And then when we get a cold front comes through and all of that cold air rushes in underneath, then we get this inversion forming. It's a classic inversion after a cold front is coming through. And then the whole cycle starts again. So obviously the environmental lapse rate is something that does vary and depends really on, and you can have sort of isothermal sections where the temperature doesn't vary with height. You can have, you know, obviously inversions where the temperature increases with height. But generally speaking, the environmental lapse rate is on average is around about 2 degrees. The dry adiabatic lapse rate, and I think it's important all of the words we understand them. Obviously lapse rate means decrease in temperature. Dry means that it's a dry air mass, it's no condensate. And adiabatic is a term that refers to no energy input or output from that system. So it's a parcel of air that is isolated effectively. And so basically as that parcel of air rises and it expands and cools, the heating change is only affecting it. So that's the reference to adiabatic. That's the definition for the term adiabatic. And we know that dry air, that is air that's like us around us now, which is dry, will cool at 3 degrees per 1,000 feet. And so that gives us these red lines. So we've all seen that. We know that a parcel of air that obviously takes off from the ground will cool at that rate. And it will continue cooling until it hits a temperature which is equal to the environmental air, the environmental lapse rate. And that's at a point where there's no further buoyancy for that thermal. It stops rising. Obviously, as the day, as the mixing occurs and as this inversion tends to move across, we have, you know, you can see here, you have a classic day where early in the morning there's a queue forming, and all of a sudden those queues start to disappear and the sky blues out. It's often because early on it's hitting the this dew point line, and then as the heating occurs, the air is warming up. It's got more capacity to hold moisture, so it doesn't form clouds. So that we then lose the queues; they all dry out and dissipate. Now, the wet adiabatic lapse rates is interesting because it effectively there is heat being released because of the condensation. And the way that works is that if you can imagine if some water is spilled on this table and you put a hairdryer onto it, that water will evaporate, it will disappear. The sensible heat from the dryer is being used to convert that moisture into water vapour. And what happens is the sensible heat, the real heat from the hairdryer, is now being stored in a latent form. Latent is Latin for hidden, and so it's hidden heat. So what happens, of course, is that heat doesn't disappear, that energy doesn't disappear while it remains in the water vapour remains in a gaseous form. If the air cools down to a point where that water starts to condense, then that latent heat is released and becomes sensible heat again, and all of a sudden we've got a warming air mass, so that or there is heat being released. So consequently, the rate at which the cooling occurs is halved. It actually goes to 1.5 degrees per 1,000 feet. And we all know what happens there is if you've got an air mass that is obviously rising and you hit that condensate point, it becomes very unstable because of that heating, that extra heating that goes into it, so QNIMs form. That heating will just continue going on because it's really never going to reach the environmental lapse rate, or it may, but obviously if the environmental lapse rate stops that, intercepts that particular 1.5 degrees, then it'll stop the air mass rising. But there are often circumstances, as we know in summer, where that air mass becomes very unstable. I think, Peter, you were going to talk about the SKU-T and P-log diagrams. So instability, obviously the sort of instability which we call ground-based instability, which is thunderstorm development, is through this wet adiabatic lapse rate. And but you can often have instability where the dew point in the air has got so much moisture in it that from sort of 10,000 feet through to 30,000 feet, all of a sudden you hit dew point, and bang, that's when we get thunderstorms and rain just from upper level instability. So there's different ways in which the stability can demonstrate itself or evolve. So I don't know, is there any questions on that? I just wanted to, rather than sort of concentrate specifically on just general weather, I thought maybe if we were to talk about some of these basic aspects that it might be of value to people. I didn't want to take too much time because I think I want to give Peter enough time to do his presentation, but just before I move on, is there any sort of questions about that? Has it been useful? That's what I want to know. And I think it might hopefully give a little bit of a better understanding of the sort of words that are bandied around and how we can perhaps use these diagrams if we, because we can still get that information on the environmental lapse rates from the temp traces that have flown out of Adelaide.
Yeah, I'll briefly flash that up later, so you'll get to see it if people haven't seen it before.
Yeah. Okay. Well, if there's no further questions, we might move on to your section, and I'll have a break, and I'll go on to my piece afterwards. Right.
Apologies if I'm not that coherent. I had to start work at 4 o'clock this morning, so I really haven't slept for a couple of days.
A little sleep you can actually
I'm not running. What I'll do is I'll do a few things. Actually, before I get into any of that, what I've inflicted on everybody else is ask them for a bio, so it's probably only fair that I inflict that on myself as well. Some of you may not know my background, certainly outside flying. Outside flying, I'm an engineer. Originally electrical engineer, went through Adelaide University and graduated in 1989. But these days I'm basically an engineering manager and work for the government as little as possible. And when I'm not flying and I'm not working, I also enjoy four-wheel driving. We've just spent 3 weeks, my wife and I spent 3 weeks in Central Australia across the Simpson Desert, all the camping out there. It was a lot of fun. I'm of course married to Mandy, the president of GFA. Getting onto flying, I started flying in 1982 with the Adelaide Uni Club. Flew with them for quite a few years, and then with a bit of transition. Since around about 1998, I've been flying with the Adelaide Soaring Club. In that time I've amassed 4,100 hours, roughly. I'm currently the head coach for South Australia and the Northern Territory, which is why I'm coordinating these lectures, and also the coaching week, which I hope you'll all go to in just after Christmas. Some years ago I was a level 2 instructor, but I've let that lapse to focus on competition flying and coaching type aspects. Might eventually get back to doing that at some stage. I've flown in 3 World Championships. They were in all of them in mountainous or semi-mountainous countries. So it was in France, Italy, and Slovakia, with the best result as a bronze medal in the Italy World Championships there. I've been national champion 6 times, due primarily to last season. I'm now the holder of 8 national records and 1 international, 1 continental record. Continental is a bit strange in this context, but by continental it's basically Australia and New Zealand. That was ratified a week or so ago. I own an ASG 29, like Craig. For my sins, I'm also the chair of the GFA Handicap Committee, so those of you that fly in competitions and want to complain about your handicaps, blame me. And I'm also the airspace officer for Adelaide Soaring Club. Enough of that. Now, what I'll talk about is some of the printed. That's rather interesting because what's on my screen is not what's up there.
Okay.
I'm not sure why that's there at all, actually.
Just say yes. Yes.
Keystone directions. When you moved the projector, it woke up and did something, so it's to do with the projector, not computer.
Just hit that set button, I reckon. That's it.
Yeah,
That's just Keystone, but that's surely you can do Keystone and not. Okay, finally you can see what I'm talking about. Right, I will talk about numerical models, but given the good introduction that Craig's given on this diagram here, I'll actually jump straight to the SQT diagram. In fact, no, before I do that, I'll show you that the sounding information, the real-time, the real sounding observations are still available. Unfortunately, these days, they don't come in early enough to be useful for that day's flying. They're too late. They don't come in until, I don't know what it is now, about lunchtime or something like that. So you've got to use the previous evenings, which means it's a bit dated. But this is real observations. It's basically that plot. The blue is the blue here. Actually, doesn't look that too dissimilar. So that's the temperature. The red there is the dew point. Also, it's got wind speed and wind direction. It's not a very good way of plotting wind direction. It's got wind direction plotted on there as well. Right, so they're real measurements. They send up a balloon from Adelaide Airport twice a day and log what comes back from it, and that is available online. I'll make the link I just clicked on. Go back to it. I'll make these slides available on the website for this lecture, or for the whole lecture series, and you'll have all these links then, so you can get to those links. So that was the sounding information there. There's also soundings for quite a number of other places around Australia available on that website. But let's look at a SQT diagram. So this diagram, as it's shown here, has altitude or pressure on that axis and temperature on that axis. This is a bit different. If you look at the temperature, which is shown on this axis down here, the lines of constant temperature are actually running out here. So it's these lines there. So it's skewed. And I haven't actually not sure what the origin of the SQT diagram, the name SQT is, but maybe that's why. But they've skewed it around, and it enables you to actually see, you extract an awful amount of, a large amount of information from this diagram, and in part it's just due to the way it's actually structured. So this is, a SQT can actually have observations for these lines, or these can actually be predicted. Right? So it could actually be the observations of the environmental lapse rate and the dew point and wind and things like that, or it can be a prediction. It can be, the diagram can be used for a lot of those. In this particular case, unfortunately the colours are reversed from what I just showed you. The red here is the environmental lapse rate, and the blue is the dew point. There are other things displayed on here as well. Depending on where you get these QT diagrams from, you may not have an altitude scale here. That's just a direct function of the pressure here, and you can convert 850 to whatever it is, 4,500 feet or something like that. It's a lot easier if you can find one of these, and I'll show you where to in a minute. That actually has that vertical scale on it there. Unfortunately, most of these go up to some ridiculous altitude, 32 or even higher, 32,000 feet or even higher. The bit we tend to be interested in is generally about the bottom 15,000 feet down here, with the exception of where we're looking at significant areas of overdevelopment or higher level cloud, because they'll show up on these diagrams as well. So if we look at the situation here, now this was actually for today, 1:30 in the afternoon. Now, when we looked at the weather today, it wasn't a particularly spectacular day. And you can see that from this diagram. This is a forecast. This is showing a number of things. Any time where the dew point matches the environmental lapse rate, like this area in here, that means you have solid cloud, in this case between about 3,000 feet and about 5,000 feet. Right, so that's cloud, all that area there, right? Because you have your dew point matching the environmental, or the temperature at that level. Provided, well actually if the lines touch, as they do here, then you do have cloud. They may be slightly displaced. If they are slightly displaced, you probably still have cloud because the temperature on the ground is actually slightly more. So the way you actually read these diagrams is if you take a temperature today, say it was, I know it was only 14 degrees or something rather cold, but say it was 20 degrees today at the ground, you follow this line here, so all the lines running on this axis here, in that direction, are following the dry adiabatic lapse rate. So that's what all these lines are there. So you take a parcel of air, heat it to 20 degrees on the ground because the sun's shining on it, or maybe it's a tractor or something like that, and it rises along, cooling as it goes, along this dry adiabatic lapse rate, until it reaches, or more or less until it reaches the environmental lapse rate. So in the absence of any cloud, you're going to get thermals going to, in this case, about 7,000 feet. If it got 20 degrees, which of course it wasn't. Today being about 14 degrees, you get almost nothing. If you want to look at the height of your cloud base, that's a pretty important piece of information you can extract from these. You take the dew point down here, and these dashed green lines running up here are the mixing lines. So that's, it's not the wet adiabatic lapse rate, but it's a mixing line. So if you take air that's, so the dew point here is looking at about, what, 9 degrees, something like that, and follow these dashed lines running up there, right, until you get to an intersection with whatever the parcel of air running up your dry adiabat is. So if you were talking about a 20 degrees here, and if it was running up here, so the intersection of that point and a dew point here, intersection of that line, dew point here, it's going to give you cloud base around about there. And in fact, that's what this is showing you anyway. Right, that's this dashed purple line. Right, so that's taken from the dew point here, following these mixing lines up until it reaches, in this case, it's the environmental lapse rate, or wherever your parcel of air's got to. Once the moisture condenses in that parcel of air, it no longer follows these mixing lines, it follows the wet adiabatic lapse rate, which is the solid green lines on here. So you can see there's a lot of information on here. So you have air at this point here, it then follows the curve of the solid lines. So you can see that this dashed purple line here is parallel to the solid green lines there. And that's showing then that you have cloud forming at that point, and it will generally, the tops of the cloud are going to be roughly where that meets the environmental lapse rate. The problem we have in summer is that this kink here, or this red line, is likely to be further to the left. And this purple line goes all the way up here somewhere. And that's thunderstorm pattern. Right, so you can see from here, if that was happening, it's not going to happen in the middle of July generally. But you can actually predict the thunderstorms. If this is also a forecast, as this one is, rather than just plotting the observed data, then there's other information on here as well, which is shown on the left over here, and that's cloud. So these black lines here is showing cloud cover, 1 being complete cloud cover, 0.5 being half cloud cover, 0 being no cloud cover. So that's saying there's no cloud down here up until about 4,000 feet. Fair bit of cloud, almost 100%, all the way up to a bit over 5,000 feet. This sort of matches what we were talking about before, and nothing above that. If we had altitude, something like that coming in later in the day, you'll see another encroachment, black line coming in up here. So there's a lot of information you can get out of this. Other information, wind speed here, shown as either barbs, wind speed and direction, shown as either barbs or on this green line here on a scale of, that's on a scale of 0 to 60 knots. So a lot of information packed into one diagram. There's probably a lot of questions on that, but we could spend the whole night on that diagram.
Well, Peter,
Sid?
yeah, Peter, you did say earlier, I think, that those graphs could be either plots of known factors, as in the environmental lapse rate, or it could be forecast figures on the lapse rate. Does it say anywhere on the graph whether it is a forecast or whether
Well, it depends where you get it from.
Yeah.
I know that this is a forecast because I got this from RASP.
Okay. But there's nowhere on the graph that actually tells you one way or the other.
In fact, I don't know of anywhere, any websites where you can actually look here. Well, it says up here 46-hour forecast up there.
Okay.
But I'm not aware of actually any websites. I don't know any websites where you can actually get this data plotted, like observation data plotted in that way. I'm just stating as a fact that you can plot
Yeah.
observed observations on this
Yeah,
chart,
okay.
but I'm not aware of anywhere we've
So-
gone in yet.
So those that we have access to are only forecasts.
Yeah, well, you got the one from Bond anyway, which is in the aviation area. Bond, that's actually observations.
That chart is plotted on SQT? Or?
Yeah.
Is it? Okay,
Yeah.
well, fine. So,
But that's done at 0 UTC, which basically means about 10:30 in the morning you get it here, which is probably a good rate.
yeah, so that's the same data as the
That's
previous
the- that's
sounding
the
that I
observed.
observed one that I showed you, but spot plot on that sort of diagram.
All the rest are predicted like that one.
Yeah. Mm. Any other questions on that?
We've got the green one on the left side as well, gives you an idea of the cloud water as well, so
Yep.
potential for rain coming out of the cloud as well. So you might say it's going to get maybe a bit wet under some too, you can see it's, you might get cloud, you might get a black line but no green, but if it's a bit of green on there and it goes up to that 1.2 on green, it's a pretty high chance you're going to get a bit wet if you're
All of these sorts of charts, and also the models that I'll quickly sort of introduce you to in a few minutes' time, really you've got to study them day to day, see what the weather did, and see whether or not what you predicted from this chart was right. Talk it through with people. I mean, I can sort of show you how to use it on here, but I can guarantee you, if you've never seen this before, you're not going to go out and do a weather forecast based on that, on what I've just told you. You kind of need to work through it with somebody and have a bit of a feedback loop as well in terms of, well, was what I kind of predicted from that actually what happened? Okay, I'll move on to just the principles of numerical weather prediction. And this is what, certainly in recent years, we've used a lot of in gliding. These are the models, or we use end products that come out of things like RASP and XC Skies and those sorts of things. And Bureau of Meteorology, of course, has a similar sort of process as well in terms of modelling as well. Bureau has a whole series of models that they use, but they've also got experts in the field that kind of know when they adjust on the fly before they put a forecast out. We don't have the luxury of being able to do that. But basically, the way that models work is a lot of this stems from a global model called GFS, which stands for Global. We've got some notes here, just to make sure we get it right. Called Global Forecast System. And there's other global models as well. So this is a model here that takes observation data. And anybody give me examples of the sorts of things that might be observed and feed into this sort of global model?
Ocean temperatures,
Well, the sounding temperatures we're just talking about. Yes. Yeah. Soil temperatures, humidity, ice, anything basically. In terms of observations feeds into that. There's a lot of different things. These models, or at least the GFS model, is a model of the atmospherics, it's a model of the oceans, it's a model of sea ice, it's a model of soil temperatures. I think there's basically 4 main models there, some of which are not really of interest to us. And it's global. It's done, because it's a global model, it's done on a fairly coarse grid. It's not particularly high resolution. I did actually look it up. It actually went to a 1/4 degree resolution in the middle of the Nationals last year, which screwed up all the weather models. But now it's about a 13 kilometre roughly grid, and it's a forecast that goes out for about 2 weeks. Beyond 7 days, it's lower resolution. I think it's 1.5 to 2 degrees, something like that, beyond 7 days. Anyway, much lower resolution. So you only get reasonable accuracy for the first sort of 7 days. I wouldn't even try 7 days. So basically, you take something like a global model, like a GFS model, and then you refine that. You can do things like, the GFS model only updates every 6 hours. So it's not only is on a fairly sparse grid, but there's only updates every 6 hours, and it only forecasts in 6-hour increments. So this model here might take that and do some interpolation between them and tell you what's actually going to happen in between. And it takes observations and other things. We should actually mention that there's other things like geography that can fit into this as well. So maybe this global model has a very simplistic view of world geometry, like major land masses and things like that. But if you have much more detailed knowledge of terrain elevations, that get to something that's of interest to us. So this WRF, which is Weather Research Forecasting Model. I don't know exactly what it does. Anyway, it's a refinement of the GFS model. Then we have BLIP map models, which stands for Boundary Layer Information Prediction. There you go, MAP. So effectively, that's what I was talking about in terms of refinement. Okay, these models have various different environments. This is saying, well, we're really only interested in the boundary layer aspects of the atmosphere, and that's what this model's about in a general sense. And then you can say, okay, well, given that we then know what the boundary layer is doing, what does it mean for gliding? What does it mean in terms of thermals and thermal strengths and shears and things like that? That's where RASP comes in. So it's this continuous refinement of models to get to something that's actually really useful for glider pilots. And then you have a series of RASP forecasts out of that. Again, same as I mentioned before, make sure you update that with the real information as you get it coming in. Just on RASP, RASP is free. It's put together. It's done on a quite a small regional basis. It's not a global model by any stretch. It might cover part of South Australia, for example. There's 2 of them that I know that cover South Australia, or only bits of South Australia. And generally, it's put together by enthusiasts or small organisations that have some spare processing power that actually actually do the processing and make these forecasts available. Depending on how often they run the processing, it might be updated once or twice or something like that a day. It's not particularly frequently. But one of the things you will see, when I'm going to show you in a minute, is that it does produce hourly forecasts of what the thermals and soaring conditions are going to be like every hour during the day, which none of the other models do. So it's actually pretty powerful. Doesn't mean it's got it right, of course, but you can see the trend from That's probably enough on that one. XE Skies came out in more recent years. I first saw it about 4 years ago, 4 or 5 years ago, something like that. Now XE Skies is not free. It's available by subscription. It's not very much. I think it's, let's write down what it is. $40 US a year. So yeah, about 55, but $40 US a year. I encourage you to have a look at it. You can get a 30-day subscription for free. And I know that some people share passwords for it as well. I won't encourage that. I've got a subscription to it. XE Skies. Again, in fact, all of the models that we use in Australia stem from GFS. Now, if you're lucky enough to be in the US, there are other models available, high resolution models in GFS, that can be used for providing forecasts, but we don't have those available to us in Australia. So it starts from GFS. They apply their magic, which they won't tell us about, in terms of what it is they're actually doing to it. What they actually do say, that it'll adjust GFS for solar radiation, vegetation and terrain elevation. And it must do some interpolation as well. Anyway, it applies black magic and produces forecasts, which again you have to correct with observations. It's a global model though, so this is for anywhere in the world. So you buy a subscription to this, you can zoom in on continents, Antarctica if you want, see what the thermal conditions are like in Antarctica at the moment, probably not very good. But it's the obviously GFS is a global model, but this just extends that and does it to the whole world. So XE Skies, the model, I have to check this, but I think it runs about every 3 hours. But I know that it actually gives you the forecasts in 3-hour increments versus the 1-hour increments that you actually get on XE Skies. And generally, they haven't been quite so good recently. But generally you get a forecast out to about 3 to 4 days. The outer days sometimes only updated every 6 or every 12 hours or so until we get a bit closer, and then I'll actually do a forecast every 3 hours. Right, so that's sort of the fundamentals of what the models actually are. So if I'm doing a weather forecast, I want to know what the weather for tomorrow is going to be like, because I want to set tasks for a conference, something like that, or just want to do my own task setting for what I want to do or something like that tomorrow. This is the sort of information, I think that probably most of what I would actually look at is actually covered by here. Bureau of Meteorology is a fantastic resource. There's all sorts of stuff in there. Just have a look around in there. There's it's being improved all the time. So obviously you're getting forecasts in there, you're getting observations in there, you're getting satellite pictures of cloud. Although for satellite pictures of cloud, I tend to use WeatherZone, simply because you can zoom in on a particular state like South Australia.
Those REST models, so there's two slightly different models, aren't they?
Yep.
Yeah.
Yeah, I'll get to what those are in a minute. So this is WeatherZone. You can have a subscription to this as well. I have from time to time. I don't at the moment. Just change the format on me. Click on satellite there. This is an image that's much like what you get from the Bureau of Meteorology, but the advantage of this one is you can actually go and click on a state like South Australia, which is a much closer view there. Also, what you can do with this is you can click a point on there. You can just play that, you'll see that animates it through. And I can click a point on there somewhere, and as it animates through, I can see how far a massive cloud moves in a particular period of time, and then you can see how quickly it's moving, and how long. This is a bit too far away at the moment, but say this was closer to Adelaide, and you're concerned about this cloud mass affecting your soaring, you can actually measure what speed that cloud's doing, what distance it is away from you, and how long it's going to likely take before it actually impacts your soaring. And that's a powerful capability to be able to do that. Don't forget the area forecast available from Air Services. I won't bother pulling that up. I mean, you could spend a whole hour just going through how to read those things because they're not straightforward. There are 2 versions of RASP available. Well, there's multiple versions available for various regions in Australia. There's 2 that I'm aware of for South Australia. One of which is this first link here. This actually has a number of RASPs for quite a few different regions across Australia. And if you click on South Australia there, it'll give you well, basically this dotted white line there is the region of coverage for this RASP. And I'll just show you the other one. That, I don't know if it still is, but was originally sponsored by Internode. Isn't that available? And then there's a paragliding enthusiast in South Australia that makes this one available just for South Australia. It does have some advantages. It has a 12 kilometre grid as well as a 36, so it's actually a higher resolution image. It's quite often inconsistent with the other RASP. Quite why? Who knows? Maybe something to do with the tuning. There's another important thing that this RASP does that the other one doesn't, is that it has these forecast soundings. So if you look at Gawler, you'll find that that looks pretty much like that diagram that I showed you earlier. That's where it came from. Right, so, and in fact, if you want to see what happens as the day progresses, when you just click on these, it just steps through in 1 hour increments and you can see what it's forecasting to happen during the day. So I'm not going to go through blow by blow here all the parameters for RASP. I just wanted to expose you to these models and that they're out there. Go have a look at those links, have a play with them. Come along to Coaching Week in it starts on 27th December to 1st of January. Because this is the sort of stuff that I and others will be going through every day. Because we'll be doing a forecast there, and we'll kind of running you through the forecast for that day, and then a bit of analysis the following day as to whether or not our forecast match reality. And it's powerful. We do that day after day after day, and you just get a really good feel for how good your forecasts are and how accurate these things are. The sorts of parameters that we have available to us in RASP are things like the strength of thermals, the buoyancy shear ratio, which is basically the ratio that I'm not sure how buoyancy is defined, but it's the ratio of the buoyancy of a thermal relative to the horizontal shear. So if your buoyancy to shear ratio is very low, that means you have very little buoyancy and a lot of shear. It's going to be very hard to work with thermals. So that's thermal updraft velocity. There's a boundary layer top here, which is the very top of a thermal. You can't get there, of course, because you've got some sink rate while you're circling, which is what this hypercritical updraft strength is about. Right, so basically, assuming that you're sinking at whatever it is, 2 knots or something like that, you can't quite get to the top of the thermal, and this will show you what the top is. And there's all sorts of other things that you can look at in here. Some of these parameters are really useful for looking at something strange that's happening in the model, and you can think, well, why is it doing that? Right? So if we look at something like today, and look at, okay, possibly it's just a westerly wind. It was a northerly today, actually. So it's a northerly wind. So why is this area here so bad today? Why is it much better up there? Okay, well, we can do a little digging. And look in here, and you'll find that one of the things that it shows is cloud base. Nope, that's not showing us anything. How about boundary level cloud cover? Right, bingo, that's the problem. Right, so this model is forecasting that there's going to be a huge amount of cloud cover. That's not. Showing 0%. Alright, this has changed since I looked at it earlier today. There you go, strange things happen in models. I thought what it was going to show me was that the reason that the thermals down in the southern region here weren't very good today was because there was a lot of cloud. There was a lot of cloud there. It's blocking the heating on the ground, and therefore the thermals in that area are not so good, better further north.
They're at 5:30 now, it's not the time skip down
Yeah, but even back here. Let's try a bit earlier. Yeah, so there's more cloud down south than there is. There's a lot of cloud up north, so I'm not sure. I don't really pay too much attention to these models at this time of year because we don't tend to go to this country climate this time of year. But certainly those sorts of things, looking at cloud cover is something I want to do in the summer flying. It'll also show the energy in the air, which is CAPE. This, I'm going to go into it here, but it'll also show wave conditions, convergences, boundary layer max up-down convergence. This is really, particularly the resolution of this model. You've got a 12 kilometre grid. If you've got a 12 kilometre grid, it's a much smaller area that it gives you, but it's really good at showing up convergences down your peninsula and the convergences that we get running up through here, up to the west of Balaclava, and also the convergence over the hills, Adelaide Hills. This model is really good for showing that, and we can use it to good effect. So that's RASP, or the two different RASPs that are available. And the Nexi skies. I'm actually logged in at the moment. If I wasn't, it would ask me to log in. I've got a couple of profiles set up, but I'll just open a profile for Gawler. Mentioned before that it was global. Let's just see that. There we go. So that's the model of what's happening all over the world, and I could actually no way. Anyway, you can zoom in on Europe or something like that and see what the weather is there. Let's just go home and go back to Gawler. Okay, timescale across the top here. Mentioned it goes out to about 4-5-ish days. It's in 3-hour increments. You can click a forecast for any of those 3-hour increments. Zoom the map to wherever you want. The sorts of parameters that you get on the left here are much the same as RASP. So the top of usable lift, the strength of your thermals, your buoyancy to shear ratios, which must use a different definition because they never match what's in RASP. CAPE, cloud-based depth, cloud cover. This one is interesting. It's got cloud cover without high and cloud cover. So if it shows you a lot of cloud cover, then you can actually differentiate between whether it's high cloud or low cloud in the picture that's on there. It also shows wind speeds and things like that. This also gives you what's called a point forecast. You just click anywhere, doesn't matter, and it'll give you a point forecast. Let's go too quickly. That's buggy. No, that's come up. Okay.
Tomorrow looks good.
Right, so for any particular point, you can select a point and it gives you a plot. You can select various parameters down here. I've selected vertical velocity. But it gives you a plot over the next, 3 days? 2-3 days? We're here, of what's actually happening to the boundary layer. The red line is the top of usable lift. The black line is the top of the thermals, and then the white line is basically sensitivity. So if your temperature is 2 degrees more, where your thermal's going to go to, a lot higher. The coloured shadings in the middle there on this plot that I've got shown there shows your thermal strength, which is almost nothing today. And it also shows you There isn't any on there at the moment, but it will also show you the cloud on there as well. This is a really useful plot for looking at the time the thermals are going to start. So if you look down here at, say you wanted to get to in summer, you're basically not going to want to fly unless the thermals are going to 2,500 to 3,000 feet. You can run across there and see what time your thermals are getting to about 3,000 feet, and you can run across here, and I tend to find that in terms of when the thermals drop off, as soon as this peak starts to drop off here, whatever time that is, 4 p.m. or something like that, is when the day is basically starting to die. So you can see from that the formation of the thermals in terms of when they start and when they're likely to finish. It's also got wind strengths, thermal strengths. It's a really useful plot. Again, it's a model, it may not be accurate, but again, it's a good starting point. So it's showing that tomorrow is actually not good, but it's an okay day. The day after is absolute crap. And then just lastly, before I close off on this, there is another feature in XE Skies. Again, at Coaching Week, we can run through this in lots more detail, but you can actually put a route forecast in. So you're going to fly from Waikerie to, somewhere east to Renmark, down south and back to Waikerie. And then you can do a route forecast, and this will give you, very slowly, a plot, much the same as what I just showed you. So if I go to vertical velocity, just so I'm consistent with the plot. So if I select time, so we wanted to start our flight at, or start our cross country at noon and finish it at 4 p.m. Refresh. Doesn't seem to change anything. Oh, it has, there it is. Okay, so that's the same plot as before. You can see as I move the cursor across there, it shows where we are on the task. So it'll show you at a particular time, at a particular location on the task, what your thermals are doing. It'd be fantastic if it was actually right. But again, these are all different bits of information that you need to put together and work out what's accurate and what's not. I won't put too much credence in this, but it's just another source of information. I should probably stop with that. I mean, obviously we could, and in fact I do a coaching week. I do it for multiple hours, just talking about these models and how to use them, how to interpret the weather from them, and those sorts of things. But I just wanted to give you a taste for this. Those of you who haven't used these models before, please do have a look at them. The links will be, hopefully in the next week or so, I'll put the links up on the website. And explore them. And the more you use them, the more familiar you become with them, and the more familiar you become with the weather and what the weather's doing. I watch the weather all the time. I look at these sorts of models, not so much this time of year, but certainly some of even if I'm not flying. I'm flying for a week, 2 weeks, something like that. Still looking at the weather every day. Still doing forecasts. Oh, buggers getting 10,000 feet today. And looking at the models, and you get good feedback. Any question on all of that? Baffled. All right, we'll take a break, and I'll tell you. So if we make it a quick break, just grab a cuppa or something like that, and we'll be back here in say 7 or 8 minutes time.
I think we've got everyone back in the room. We'll kick off. As I was just saying to Peter, this particular talk is more, I guess, orientated to people that are new to cross-country flying. But mindful again that we've got some very experienced people in the room that perhaps will throw in some experience that I've had at least over the last few years. It's a talk that I put together some time ago in terms of task planning, and really from my experience going back to, I fully remember this, the very first cross-country course that we ran at Waikerie, Mark Morgan and Terry Moore I think were doing it. The one thing that sticks in my mind from those was the fact of preparation, of actually getting ourselves to a point where we could get in the air on time. And I think everyone suffers from that, is actually being able to launch at a time that enables you to do the task that you want to do on that day. And I think even now we still suffer from that, of you know, you sort of get to the airfield in the morning at 9 o'clock and think, gee, today's going to be a fantastic day, and you've only got 1 hour before you're going to want to be in the air to do that 750k task, or a 500 or whatever it is that you want to do for you know, your particular flying capability. So I can remember on that was, you know, Mark Morgan in his usual form was extremely frustrated with us as students, and so what he did was got us out there, and before the lecture started at 9 o'clock in the morning, I think it was around 8 a.m, we were to get out there, get the gliders out, get them DI'd. And that, I think I've sort of kept that in my memory and my mode of operation, is to try and do as much of that preparation beforehand as possible. So I guess for those people who are experienced, they probably know all of this anyway, but you know, there are so many things that you can do, say the night before. Obviously with the weather models that are available, you can see a good day coming up, you can start thinking about the tasks in the area that you want to fly into. So there's a whole lot of things that we can do to ease the tension on the day, so that we're not quite as flustered by the time we get into the cockpit and try and head off for that 1,000k task. So it really is all about preparation. That's the one thing hopefully that you'll get out of this talk tonight. But anyway, the art of cross-country flying, obviously we all need to be able to be good pilots and get to that next thermal and sort of achieve a cross-country flight. But really the ability to do the longer flights is all about planning. It's all about determining what the weather's going to be and being prepared so that you can use your good flying skills to actually achieve the distances you want on the day, to actually push yourself out to those longer boundaries. And you know, I'm sure that if we put some of these things into practice and we can actually be on the grid a little bit earlier, then we might achieve some of the longer flights that you want to do when the good day comes along. So if we have a look at some of the sort of the organisation that's required, the tasks that you know, need to be completed, I think you can see there's a large number of things that need to be done, and you know, the number of times that you kind of focused on getting things done, and then people turn up at the airfield and say hi and how are you going, and want to have a 10 or 15 minute chat. You've really got to be disciplined and say sorry and keep your focus going, and actually make sure that you don't lose your train of thought. You've got to process in your mind and you keep on with those tasks and keep pushing yourself. So all of the things that you've got to try and do in the morning before you're actually on the grid, in terms of setting the glider up and attending the morning briefings, having some form of decision about where you're going to fly for the day once the weather forecast is done, getting the water ballast into your glider, organising data loggers, getting something to eat, making sure that all the stuff is in your glider, just relaxing, getting the toilet, and then you're in the plane and away you go. So that transition, which I always find quite amazing, is that you're on the ground running around and doing all of these things, and all of a sudden you're in the cockpit, the canopy's closed, the rope's going tight, and your mindset's got to change all of a sudden. So there's a lot of organisational skills that put you in a position where you're in that cockpit at that point of launch, you're ready to go, switched on, and able to get that task done. So again, it's all about that preparation beforehand. Can't overemphasise that. So really, how to get that preparation done is starting early. I think one of the things that you should be doing the night before, particularly with the weather models that we have, is actually starting to think about some of the tasks that you want to do, the directions you want to go. At Waikerie, we often look with envy over towards to Gawler and seeing the convection going up the hills, and we call those far queues, and then we get to them. But again, it's the days in Waikerie where okay, the hills are going to go, and we're probably going to get enough height to connect with those. There's probably not a lot of point going east because it's going to be really good in that direction, and maybe we can come back and it'll be great in the east. And so what you're starting to do the night before you start to have some idea of where you're going to go. And of course you can modify those plans on the day itself, but certainly with the longer tasks. And Peter, that day in January, 4th of January, was the fire day, wasn't it?
Yeah, second of January.
2nd January. So I'd be right in saying that you kind of had that worked out the night before. I certainly had an idea of where I was.
I had the task plan 5 days before.
5 days before. Yeah. So I think, certainly those longer tasks, you really need to have those ready to go. I suppose it's less critical with 300k tasks or tasks below that distance. Certainly you can maybe pick those on the day, but if you're ever going to do a long task, you need to have everything pretty much ready to go, maybe sometimes the day before.
How long does it take to do a 300k task?
3 hours, 4 hours.
35 hours, I suppose.
How long do
Well, 300 take me, 6
it? I was conscious that for a big task for you and your glider doing 1,000k, you're looking at 8 or 9 hours, so that's a huge task. But even for somebody doing that 300, it could be a 5 or 6 hour task, so it's still a big task.
Yes, and I guess that's where the rest of this talk goes, is planning decisions of how far to fly and where to fly. Right? So the how far to fly bit, as Terry's alluding to, is really based on your own cross-country speed ability. And I know when I started cross-country flying, when I was flying, I think in the Hornet, I know Astia, the Astia CS. I think my best average speed at that time for Blanchetown and return was 67 kph. Right? So that's what I could achieve because I took every thermal, I worked weak thermals, and certainly I know in the club class competition on that strong day, which again was a bushfire day on Eyre Peninsula, I flew the club discus and I flew a good speed for me, which was 105 kilometres an hour, but you, Terry, did 149. And I kind of wondered where the rest of the 40 kph an hour was going to come from me. It was 3, that's right. But the thing is that no matter what stage you're at, then you're going to know what speed you're capable of on a given thermal strength day, and that's the thing that does vary is obviously the sort of the height prediction, and clearly the higher it goes, the stronger the thermals are, the faster your cross-country speed is likely to be. But certainly, if you know what your capability is on that day for the altitude, and we know from what Peter just showed us the length of the day, then we know how far you can fly on that day. It just tells you what you're capable of flying on that particular day. And I can well remember the day I did it, my first 500k task was a pearler of a day, 10,000 feet. I was in the discus, and it took me all bloody day to do it. And there was a guy on the ASW 22 that did 1,000 k's, and I just had no idea where that extra 500 k's was going to come from. Even still, but the thing is though that I think as you get on, your experience improves. You tend to fly faster, and all of a sudden those extra distances will open up to you. But I think the point that Terry makes is very good. Is that obviously if I'm planning a 1,000k task, you might be planning a 300, but they're in a sense equally as difficult. 1,000k is be difficult for me. 300k task will be difficult for someone that's perhaps just starting out in the sport. But that equation really is what you need to work with. And so, looking at different strengths of the day, as the thermal strength increases, our cruise speed will increase, our cross-country speed will increase. So, these are theoretical achievable, dry and the discus, with those sorts of thermal strengths. So you can see that, you can match yourself against some of these, this data and see how you're performing in terms of your efficiency between on certain cross-country flights. And obviously if you're a day where someone else is achieving 5 knots average climb rate and you're only getting 3, well then clearly there's an issue there where perhaps you're not using the thermals centering as efficiently or using the best thermals that are available on the day. But at the end of the day, the cross-country speed that you're able to achieve, the length of the day will tell you how far you can go. So those are the sort of things that you need to keep in mind when you're planning a task the night before or in the morning as to where you want to go and how far you want to go. But as you gain experience, that distance will increase. So I guess really the thing that I spent a lot of time at was the bottom line was trying to increase my personal flying speed. I think I bashed around the Waikerie Peepinga Lindsay River task a number of times. I think I know most of the thermal spots around that. But again, it was just simply, when I was flying the Hornet, and I remember that date I did 600 Ks, I actually did the task twice to get the 600 Ks. But again, it was just really persevering with that flying to get up to that speed. And I think really at that point I was trying to fly the Hornet at an average speed of 100 kph to get to that point, you see. So, but again, as you gain experience, then you're going to get faster. So I already talked about weather forecasting, and clearly with the models that are available nowadays, it's a lot better. You know, I can remember people had the best they had was looking at Area 50 forecasts in Victoria. You know, we had weather traces in South Australia, but when we were doing 1,000 k tasks of taking out to Kerrang or Swan Hill, then you know all of a sudden you're going off into the unknown. But nowadays with the weather forecasts, you really should be able to estimate, you know, how high it's going to go and what the length of the day is in the flying area. So the result of all of that, you should know exactly what you're going to be able to achieve on the day. What we then try and do once we've got the task in mind is to make sure, again, preparation, that we get to the grid at the starting point. We know when the convection's going to start, be on the grid for it. Don't be out there an hour late, you know, when it's already been going and you could have been flying for that extra time, because, you know, if you've got a long task that's very marginal for your capabilities, then you're not going to make it. So again, it's all about, you know, working out when you want to start, when the convection's going to be starting, and trying to be there and be in the air as soon as you can. Once you take the launch, then you know it's I guess unless you're doing a 1,000 k task, and I remember when watching you at a long way down, just heading off. When you're doing the longer tasks, you need to just head off and hope that things will get better. But certainly for some of the shorter tasks, it's probably a good idea to actually be around the airfield, experience the thermal conditions to see that they're actually matching what was forecast, that you're actually able to achieve the height, and you know, obviously you get to the point where you feel comfortable with what the day is providing, then off we go. So again, once you're out on task, what you need to be doing is really assessing whether or not the day is performing as should be, or perhaps there's some anomaly with the weather. I know that on the day that we flew, I got to about Swan Hill. It's a long way back to Waikerie at 5 p.m. in the evening, and to be sort of thinking about going out to Hay, and with the prospect of then 400 k's back to Waikerie, I made a decision at that point that it was better really to head back to where the good air was, to make sure I was going to be back at Waikerie. I then ended up sort of, you know, travelling well out past the Gums and then back to Waikerie, which gave me the distance. It's probably just really an easy 1,000 k's, nothing planned, but certainly at some point, if things are turning to worms, you've got to recognise that, otherwise you could find yourself a long way from home with no real prospects of perhaps getting back with an outlanding. And I guess really I remember the 750 that I did in the Mosquito. I was out at Peterborough very late in the evening. We were fighting against some headwinds, and I thought, well, I might as well get to that last turn point and see what happens. If I outland, I outland, but you know, I'm sort of going to be in good territory if I do. And that pays off, because you know there was enough lift around to actually get me back. So maybe sometimes it's better to push on and try and get to that last turn point rather than giving up, thinking that, well, if you do get jagged good conditions, you'll get the task, you get the 750 k under your belt. If not, if all turns to worms, then you know, you're going to outland. So. And then I guess really once you've completed the flight, the best thing you can do, particularly if you're flying with other people on the day, and that's the value of flying, I guess, in competitions, is to be able to look at what other people are achieving, to match yourself against other people's standards. and you know, with the systems, computer programs that are available now, they're a great way of evaluating, particularly if you've got you know, coaches that you can evaluate with, to analyse what you've been doing on the day, whether or not you're achieving the sort of climb rates that others are, so that you can start to gauge where you're at in terms of performance. I hope all that helps. Questions?
Craig, you had a spreadsheet on the discus interthermal speeds and average speed C to work out distances you might fly with the time you've got. You came up with that chart by reading it off of
Just the polar curve.
polar curve. Yeah.
Just the polar curve, and I think, I mean, it's in terms of interthermal speeds, I think it's well known that, you know, there's a huge range, speed range for a given thermal strength in the day that you can be flying either side of. It doesn't really make a lot of difference on your achieved cross-country speed. So, you know, those figures are, you know, if it's sort of 5 to 10 knots either side of it, it's not really going to make a lot of difference in the achieved cross-country speed.
Yeah, would it be true to say that all the things you need to do in preparation for a long cross-country flight, task planning, all the rest of it, glide preparation, all that kind of thing, actually takes a lot longer than you think it will? Therefore, you need to start planning the previous day. What you said, merely rocking up at the start of the day to the club and thinking, oh, this is a great day for doing it at 500 or whatever, considering that you've then got all the glider preparation to do, probably won't quite cut it.
Well, you're exactly right, and you know, that was the experience that we had in the basic cross country. Is that, you know, we were all faffing around for so much that, you know, the day was going at 1 o'clock and we're still on the ground at 2, not ready to launch. So, you know, a number of times I've seen guys that at the end of the day missed their 750 by 20 kilometres.
Yep.
Because they weren't in the air, you know, for the half an hour beforehand that they could have been. So, and I think you do get used to what needs to be done. There's sort of, I know that I'm very much in a routine. I like to do certain things in certain orders. Before the briefing, for example, I like to get water into my glider. I like the glider at the watering point and ballasted and de-eyed and all of those sorts of things done before you go to briefing. And then you can come back and start fiddling around, putting the tasks into the computer, get yourself settled, have lunch, final preparations before then towing out on the grid. So it's sort of it's a real system you've got, particularly all the things in the hangar that you want to do, putting water into the water bag, making sure the fuel's into the glider, all of those sorts of things are just something that you get used to if you, particularly if you're flying the same glider all the time. You've got a real routine and you kind of know what needs to be done. I think the things that perhaps throw you are when things go wrong, if something breaks or fails. I will remember you towing out the Aussie one time.
Yeah,
some
broken
difficulties
wheel
with that.
bolt. Yeah.
That's right. So, you know, it's all those little things that unfortunately can't do much about that might throw a spanner in the works, but as best you can, preparation hopefully will overcome some of those issues.
All that still takes a long time though. It doesn't just happen like that.
Yeah, and I think, you know, certainly for me, it's a bit of a shock trying to think, well, I'm going to do a long task today, and I actually got to be ready by 10 o'clock. It's really quite different to, you know, thinking a 1 o'clock launch. You know, and, so it's just a whole different mindset. If you want to do these longer tasks, you've got to be prepared to push the boundaries, be out there a bit earlier than what you ordinarily would.
You also get the tow pilot ready.
Hopefully that's in order, yeah. But I think also, you know, I find it amazing, it's the constant distractions, and you really have to be a bit brutal with people. You know, if suddenly someone rocks up and you haven't seen them for a week and they want to start chatting, you've really got to be a little bit harsh and say, a bit focused here, sorry, and keep pushing on. Otherwise, you will get time soaked up, and just will force you to be a bit later, I suppose.
I'd say practice preparation. Even if you're not going to go off and do a task, have the mindset that is if you are going to do it, get yourself ready, just go through the motions. People find if you've never done it before, you'll find it takes you a lot longer than what you think it might.
I think also that, you know,
once you've got yourself set and go through that a few times, when you're going to do it in anger, you'll find you won't play the day, because you've already done all the hard work beforehand. So routine, get through there, keep doing it. Yeah.
And it's not only that sort of daily or the weekly process. It's you know, it's probably happens over ebbs and flows over the year. So you know, the last cross country flight that I did of any significance was in February of this year, and I've flown my glider subsequently to that, but you know, just sort of to shake the cobwebs out. So you find yourself getting into September, all of a sudden having to get the mindset back again and gee, see you, oh that's right, I know that program. Oh, my data logger, where's that? You know, and so the September is that process where again you start to get yourself back into that routine. And certainly I know I've had the experience where we've done a lot of flying before the flying season, before a competition, and you go into it well prepared. I've also had the circumstance where the glider wasn't available and I had a new instrument in there, and I had a Nationals that was just absolutely abysmal. You know, the LX system in there, and it wasn't working, and I didn't know how to use it properly. I remember one day flying the task with my wheel down, the whole task. I had the radio turned down because all these people were squawking in the box, and they're all trying to tell me to put my wheel up. But, the reason that happened was because of the distraction of not knowing how to use my logger properly. And I turned it off before I'd saved the task, and when I got into the air I had yesterday's task in it. And then I had to put my head down in the cockpit, which was like go away somewhere, and that was, I realised that on tow, and of course the routine was broken, and that routine of pulling the wheel up and the like had all gone, and my mind was elsewhere. It was a total distraction. And one thing I forgot to do was to change the start point back to where from the previous day to this day, so it didn't really matter that the wheel was down anyway, because I just didn't fly. I didn't get a start. So, you know, I think that's a classic example of you know, it's one thing to be proficient with the glider and you know, be flying it regularly from week to week like you're saying, but there's also that seasonal transition from winter into the flying season that you've got to ease yourself back into it and start reminding yourself about you know, just the mechanics of putting in tasks and let alone actually flying them accurately and efficiently. But again, it's all about preparation, and certainly we've got a little group at Waikerie which is you know, in preparation for this year's multi-class nationals, where we will be putting you know, some effort into at least on you know, a regular basis every fortnight of just you know, as a group getting together and talking about task preparation, flying tasks, analysing them over that evening, so with a view to being very current by the time we hit Christmas, hopefully going into the comps and without any sort of rust on either us or the glider.
Do you have your own checklist as club flying and going away?
Oh, certainly going away. Yeah.
Yourself, yeah.
Yeah, I've got. One of the trips that we do quite regularly is the Horsham Loop, and apart from the wine glasses and wine bottles and checklists, I think Greg won't mind me saying this, but Mandy once had to put the maintenance release on the bus to Horsham. I know that this year gone past, there was someone that turned up without a wheel walker, a wing walker. So yeah, the checklist is just critical. Absolutely, I mean, you know, to make sure that when you're going away on competitions or taking your glider somewhere, that you actually got everything you need, right down to battery charges, to wheel jacks, to everything. You know, so that really helps. On a sort of day-to-day basis, I don't tend to necessarily use the checklist mainly because, as I said, I've got a real set routine that I kind of stick to, doing certain things at a certain time. That seems to get me by. And you do, on a daily basis, it starts to become a lot easier to just remember it, and it all happens, particularly flying a 2-week comp. I think coming into the comp, you should be in a position where you're really familiar with your equipment glider, and during the comp, you just get even better, I think.
From a practice perspective, I used to find that I was going to practice wanted to do a 300-kilometre flight or something, and the weather wasn't quite good enough. You can actually practice doing the first part of the first leg, and then the last part of the last leg is not just to get used to where you are and what you're looking at. And I found that made a big difference in terms of confidence that you know where you are. I think that sort of stuff, in terms of practicing and preparing, I think that's quite good fun.
No, well, it's obviously, you know, in terms of those people that are new to the sport, there's nothing better, I think, in terms of training, particularly thermal centering, is to fly into the thermal centre and fly out of it, fly a kilometre out, turn around, come back in again, find that same thermal, go through the whole process again. Do it as many times as you can so you get used to what your glider's telling you in respect of when you're entering that thermal and knowing when you've actually hit the core, not the sort of lift before the core. So hopefully that's a benefit. Again, I've got to apologise for this facility not being available. It would have been if I was here. But certainly next year if we're running it at...
I can help with that. I can help with that. So I can do some type of representation of your person here next month. That's okay.
So I think you want the key to the door, isn't it?
You still on the card, you said?
No, get back to me.
No, that's the only problem. I guess just in terms of insurance, and we need to have me along here who's someone from the firm. So again, apologise for that. Next year should be better.
Okay, if you can join me in thanking Craig for his presentation. Stand by for next month's lecture, which I think is the 12th of August, at a location to be advised and topics to be advised. It'll be good, whatever.